Okay, so good morning everyone. We are now recording. Um, are there any other questions or clarifications required for the assignment or preceding lectures? Okay. If not, then let's do a quick recap. So we are going to talk about non-separable graphs today, which is everything in sections 5.1 to 5.3 of the textbook. We will cover as much as we can, of course, and we will continue the rest on Monday. But yeah, there'll be things I will omit. There'll be proofs I may omit, and I will give it to you as a do-it-yourself assignment. Okay, so we discussed what a cut vertex of a graph is. It's any vertex such that when you delete the vertex, you will get at least two components if the original graph is connected, right? And if the graph is not necessarily connected, then the number of components should increase. So here V is a cut vertex. Okay. Good. And we know that a graph is connected if and only if there exists a UV path between any two distinct U and V vertices. Okay. So in the same sense, in the same spirit, if a graph does not have cut vertices, then a stronger statement is true, which is that any two distinct U and V belong to two internally disjoint paths. So if this is U and this is V, then you can find two paths between them that do not share any vertices except U and V, which are the ends of the paths. Okay. And of course, this is the same as saying U and V belong to a common cycle, right? So in the case of two internally disjoint paths, it's the same as saying that the two vertices belong to a common cycle. UV participate in a common cycle, right? Okay, good. All right, so let's prove the statement. So, well, let's first do the easy direction. Okay. Supposing the graph has a cut vertex. So I'm going to prove the contrapositive, right? Let's suppose the graph has a cut vertex. Let's say W. Okay. Now, well, there are going to be at least two components. We are assuming that the original graph is connected. So there are going to be at least two components, right? H1 and H2. Take a vertex U here and take a vertex V here. Observe that any path between U and V must necessarily use the vertex W. Therefore, you cannot get two paths that both do not use the vertex W. Right? So that's easy. Okay, and I won't write down all the details. Let's go to the forward direction. Is the reverse direction clear? We are assuming that there is a cut vertex W, and now take U in one component and V in another component of G minus W. Okay, good. So let's prove the forward direction, and we are going to proceed by induction on the distance between the two vertices. Right, so the distance is the length of the shortest path between the two vertices, and the path exists because the graph is connected. Okay, so the base case, if you like, is when the two vertices are adjacent. The distance between them is equal to 1, which is only possible when the two vertices are connected by an edge. Okay, so we're going to use a simple fact here. Which is that the graph G has no cut edge. We are assuming that the graph has no cut vertex. We are assuming that the graph has no cut vertex. And we want to prove that there are two disjoint paths, right? We will show that the graph can also not have a cut edge. Can anybody tell me why the graph cannot have a cut edge?
Because then at least one of the two, one of either u or v would be a cut vertex.
Exactly. Because the graph has at least 3 vertices, one of these two components that you see here, h1 and h2, the components of G minus E, one of them has to have another vertex. Let's say this one has another vertex because the graph has at least 3 vertices. Now observe that V is a cut vertex. Okay. So if you have a cut edge, then you also have a cut vertex. And you need the assumption that the graph has at least 3 vertices. Okay. So this implies that E is not a cut edge. Okay. E is the edge joining U and V. Then I can remove this edge and look at the remaining graph. The remaining graph is connected because E is not a cut edge. Therefore, there is a path between them. And now you put in the edge E, and that is another path, right? So you get two paths. E is one path, and the other path is P in G minus E. Okay? So, which implies that G minus E has a UV path P, and now P comma E are internally disjoint UV paths. Okay, good. So now we go to the induction step. Supposing I have two vertices, U and V, at a distance of K, where K is at least 2, and assume the statement, assume that the conclusion holds for any two vertices at distance less than K. Okay? So we have these two vertices U and V. All right. So the distance between them is K, which means that there is a path between them of length K. Right? On that path, take the vertex that comes just before V and call it V prime. This is a vertex for which the distance between U and V, V prime, is equal to K minus 1. Right? If you take the one vertex which precedes V on such a path of length K, then the distance between U and that vertex will be exactly K minus 1. Right? Okay. So there exists V prime, there exists a vertex V prime such that the distance between U and V prime is K minus 1. Okay. So let me erase this drawing. So we have got these three vertices, U, V, and we have got this guy called V prime. Right? Okay. So we want to prove that there are two paths, there are two internally disjoint paths between U and V. How should we go about from here? Can anyone help me out? How do we proceed from here? Well, we want to apply the induction hypothesis, right? So what can we say by the induction hypothesis? We can get two paths between U and V prime, right? P prime and Q prime. Yeah. So we can get these two paths. Let me use some colors here. So let's say I got this red colored path, P prime, and let's say I get this blue colored path Q prime. Okay, good. But we want to find the paths between U and V, right? And we have this edge here joining V and V prime. By the way, we chose V prime, right? I think I should include that here such that the distance is K minus 1 and V prime V is an edge of the graph, right? And we went through why such a vertex exists. You take a shortest path and you take the vertex before V on that path. Okay, good. So now how do we complete the proof from here? Remember, we know that the graph has no cut vertex. So we'll delete a vertex here and then look at the remaining graph. So what vertex should we delete? Anyone? What should we delete?
V prime.
V prime. Okay, great. Consider the graph G minus V prime. Okay? This is connected because we have no cut vertex in the graph, right? Okay, great. So now in this graph, there exists a path. There exists a path, let's say R prime between U and V, right? So let's take a look at this path. So let's first look at the nice case, the not complicated case. Supposing this green colored path R prime just looks like that. This would be great, right? If it does not interfere with P prime and Q prime, then you would just take R prime and you would take maybe Q prime along with this edge V prime V and you would be done, right? So that's the nice case when the path R prime does not mess with the paths P prime and Q prime. The problem, of course, is that this path may not look so nice. And so this green colored path could look like this. It could meet these paths and eventually go here. Okay. Now what should we do? Can anyone suggest what we do in this case?
So we can travel along the green path, and then whenever we intersect the blue path, we can take the this red shortcut. Something like that, so that we never meet any of the vertices in the Q.
Right. Okay, so that you're going in the right direction. So we just need to make it precise. It seems here that we should still be able to get the job done, right? So what we'll do is look at the last point where R prime meets P prime or Q prime. So in this drawing, look at this vertex here. This is the last time that R prime meets P prime or Q prime, right? And now using this vertex, I should be able to find the two paths precisely the way you suggested. So can anyone tell me what the two paths are now? Supposing this is my vertex Z, which is the last point where the path R prime. So let Z denote the last vertex on R prime. So again, when you say first and last, you need to define a traversal direction. This is the last vertex on R prime, traversing from, let's say, U to V, right? So it's its closest to V. That is what I mean by last vertex, such that Z is also a vertex of P prime or a vertex of Q prime. Yes, Kalyani, you have a suggestion as well? Yes. We can go from U to Z via the red path and then use the green path. Exactly. So yes, thanks. So that's exactly what we are going to do. We are going to use, in this case, well, we may assume without loss of generality, or I like to say adjust notation, so that Z belongs to the vertices of P prime. So I can relabel P prime and Q prime so that Z is on P prime. Okay. And now, as Kalyani suggested, we are going to take the path P prime from U to Z, right? So we are going to take this path and then take the path from Z to V on R prime. And our second path is going to be just Q prime with the last edge V prime V. Okay. So let P denote, so I'm going to introduce some notation here in this proof. So I want you to pay attention to this notation. So I'm going to define a path P, which is the path P prime starting from the vertex U up to Z. And from Z, I'm going to take the path R prime up to the vertex V. Okay. And I'm going to define Q as the path Q prime from U up to V prime. And then I'm going to add an edge to it, V prime V. Okay. So what are the two paths again? This is, I'm going to use a squiggly line, let's say. This is the path P, and this is the path Q. Okay. And observe that these two paths are internally disjoint. These are internally disjoint UV paths. And that completes the proof. Is this proof clear?
Sir, I had a clarification.
Yes, go ahead, Surya.
So what exactly is G minus V prime?
What exactly is G minus V prime?
Yes,
You
sir.
mean this? It is the graph obtained by deleting the vertex V prime from the graph G. Right? So we are going to delete this vertex and we are going to look at the remaining graph. When you delete a vertex, you also delete all the edges incident at that vertex.
Okay.
Yeah?
Yes, sir.
Okay, thank you. Any other questions or clarifications? All right. If not, then that's our proof. Okay. Good. So let us demarcate here. Let me go back to the black colored pen. All right. So, good. So that's our theorem pertaining to a graph without cut vertices. But now I want to tell you about a slight generalization of a cut vertex. And I have a new idea of how to motivate it. So let me draw an example here. Okay, so this is going to be a slightly big example, but I just want to give you enough variety to see what's going on. So let's see. Okay, so let's look at this graph. No, I want to make it slightly more complicated because I want to deal with all graphs and not just simple graphs. Okay, so let's look at this graph here. You've got some parallel edges, you've got some loops. Okay, so let's consider this graph here. So let's look at all the cut vertices of this graph. Well, this is a cut vertex. This one here is a cut vertex. So let's see, V1, V2, V3 is a cut vertex, right? Whenever you delete the vertex, you'll get at least two components. V4 is a cut vertex. V5 is a cut vertex. Okay, good. Okay, so these are the cut vertices of the graph. Okay. But I want to define a related concept which is more useful when you allow loops in a graph. And if you want the theory to work for graphs with loops, you need to introduce a slightly more general definition. Okay, so we are going to introduce a generalization of cut vertices called separating vertices. And the main point is to deal with loops. Okay, in particular, all cut vertices are separating vertices, but separating vertices are a bit more general. So all cut vertices are separating vertices. And I haven't yet defined separating vertices, I'm aware of that. But I just want you to keep in mind that it's going to be a generalization of cut vertices. Okay, so here is one way to think about this notion that I want to tell you about. Let me just take a look at the time. Okay. Okay, so what I want you to do is, I want you to think of this model. So it's, this is intuition, right? I'm not going to write down this stuff rigorously. So think of your graph as a physical model made out of beads and strings. So each vertex is a bead, like a necklace, right? And every edge is a string connecting two beads. Okay. Now, what is a cut vertex? So we are dealing with connected graphs here. Okay. What is a cut vertex? It is a vertex so that if you were to cut the graph around that bead, the bead corresponding to that vertex, then your graph would break into at least two pieces. Let me give you an example, a smaller example first of all. Supposing you look at this graph here. So what I want you to do is, I want you to think of this bead and string model, and you want to cut around a vertex. So if I put a cut here, I put a cut here, and I put a cut here. Again, I'm not using cut in the graph theory sense. I'm using cut like a scissor, right? So I'm going to cut with a scissor around this vertex. And what happens is, the graph will break into two pieces. Of course, the vertex itself is going to be one piece, but I'm going to ignore that. Another piece will be this stuff here. So it will be like this. You will have something like this hanging around, and you will have another part of the graph like this. Okay, when you use a scissor to cut around the vertex. Okay, good. Does everybody agree that this is equivalent? This is an equivalent way of thinking about the cut vertex. If you use a scissor and you cut around that vertex, the graph will break into at least two pieces. Okay, good. But now I want you to think of the following. What about this graph? Supposing I were to use the same scissor analogy, scissor cutting analogy, do you think this graph has a cut vertex? I want to use this scissor analogy. Okay, I don't want to use the rigorous definition of cut vertices, because as per the rigorous definition, there is no cut vertex in this graph. But I want you to think about this scissor analogy. Do you think there is a vertex so that when you use scissors to cut around that vertex, the graph will break into two pieces? Yes. And can you tell me which one it is, Joe?
So U and the edge adjoined to it, and the loop
Right.
edge of V.
Right, exactly. Okay, thanks. So you want to put cuts here. You want to use a scissor to cut around here. And when you do that, your graph will look like this. Of course, it's not a graph as per the definition, because a graph cannot just have edges hanging without vertices. But you get the idea. I'm trying to deliver the intuition here. Okay. And so in this sense, we are going to think of V as a separating vertex. Okay, so it's like a cut vertex, but it's more general. Okay, and if you use that definition in this example, then this vertex here, V6, is a separating vertex, but not a cut vertex. As per the definition of cut vertex, it is not a cut vertex, but it is a separating vertex. Okay, so let's write down a formal definition of a separating vertex instead of this scissor cutting business. So a vertex V is a separating vertex of a graph G, of course, if the graph G can be written as G1 union G2. So it's a union of two graphs such that the only common vertex is the vertex V itself. Okay? And there are no common edges. So to give you an example, here in this graph, I could write G as the union of this graph. V is a common vertex, and the union of this graph. Okay, so I have not formally defined unions of graphs before, but now I'm defining it, and it is exactly the way you see, right? So you take the union of the vertex set and you take the union of the edge set, right? And of course, if you want to do this rigorously, you need to label vertices and make sure you know which vertices are common, etc. Right? So if you can write down your graph as a union of two subgraphs which have exactly one vertex in common and no edges in common, then such a vertex which is in common between those two subgraphs is a separating vertex. And notice that all cut vertices are separating vertices. I'll leave that to you as an easy exercise. But there could be separating vertices which are not cut vertices. And the only such case that arises is when your vertex is incident with a loop. Okay? Of course, your vertex may be incident with a loop and it may already be a cut vertex because of other components in the graph. But here is an example, V6, where this is a separating vertex but not a cut vertex. Okay, so is the notion of a separating vertex clear? And of course, as we write down the theorems, you will see why you need this more general notion. But is the definition and the intuition sort of clear? Okay. All right, so in that case, let us move on. Okay, and now we are going to define a non-separable graph. A graph is non-separable if it is connected and has no separating vertices. Okay, good. So let's just write down all the non-separable graphs of order 1 and 2 because they are very simple. So order 1, you could have a single vertex, K1. You could have K1 with a loop. What about two loops? Is this a non-separable graph or is this a separable graph? What about two loops? Separable, thank you. Yes, it is separable because you can take the union of two graphs, one with one loop and the other with the other loop. Okay. So this is separable, so we are going to remove it. And the only non-separable graph on two vertices is K2. The moment you add a loop, you get a separable graph like the one here. Okay. So on 1 and 2 vertices, there are just these 3 non-separable graphs. And an observation that follows immediately is that all non-trivial non-separable graphs are loopless. All non-trivial. So by non-trivial, I want to remind you, I mean order at least 3. All non-trivial non-separable graphs. Actually, sorry. Non-trivial means order at least 2. Let me stick to Bondi Murthy. Are loopless. Okay. And I want to put in one more observation. It's about a definition I have not given to you yet. So whenever you have a graph like this, which is a graph with multiple edges and loops, it is often useful because in many problems and many topics of graph theory, multiple edges and loops don't matter. So what might happen in those areas of graph theory is that a graph has a certain property if and only if the underlying simple graph has the same property. So when I say underlying simple graph, it means you just throw away all the multiple edges and loops. In the case of multiple, I used to call them parallel edges. Now I'm calling them multiple edges. My bad. In the case of parallel edges, what you would do is you would replace it by a single edge joining the 2 vertices. And whenever you have a loop, you would just throw it away. So the underlying simple graph for this graph, let me just quickly draw it for you. Okay, so this is the, if I didn't miss anything, then this is the underlying simple graph of G. So this terminology will be useful sometimes, where G is your given graph. Okay. So another observation I want to point out is in a loopless graph, being non-separable is the same as saying that the underlying simple graph is non-separable. A loopless, in other words, multiple edges or parallel edges don't play any role in non-separability. Right? So the graph is non-separable if you can throw away all the parallel edges and the remaining graph is non-separable. Okay. So another way to say is parallel edges are irrelevant. Okay. Good. All right. So are there any questions at this point regarding the definition of separating vertices, separable graphs, non-separable graphs, etc.? Of course, it will become more clear as we prove statements, right? But it's essentially a generalization of cut vertices to deal with graphs that have loops. Okay, so that all the theorems extend nicely for this family of graphs. Okay, so that brings us to our second theorem. A connected graph is non-separable if and only if any two of its edges participate in a common cycle. Notice that in theorem 5.1, we were talking about two vertices belonging to a common cycle, which is the same as saying that there are two internally disjoint paths between them. Here we are talking about two edges belonging to a common cycle, right? And it is not implied by the fact that two vertices belong to a common cycle. But we will use that theorem nonetheless. Okay. So for example, if I give you two edges and you just apply theorem 5.1 to one vertex here and another vertex here, then what could happen is your cycle could look like this, and it may not contain any of these two edges. Right? So you can't just directly apply theorem 5.1 and be done. But there is actually a trick which you can use and then apply theorem 5.1 to prove the statement. Okay. So, okay, so that's the point I wanted to make. So let's write down a proof of this. So let's first prove the converse direction. Okay, supposing the graph is separable, so I'm proving the contrapositive, right? Let's say the graph is separable. Suppose G is separable, right? So one way to visualize separable graphs is that you can write it, so you use this definition, right? So this is a nice way to think about a separable graph, this drawing. You take the two graphs, there is one vertex in common, and everything else either belongs to G1 or belongs to G2. Okay? Well, so let's deal with one very easy case. Supposing there is a loop incident at this vertex. Okay? Well, then it's actually very straightforward. You take this loop and you take any edge on the other side, and these two edges do not belong to a common cycle because a loop does not belong to a cycle with any other edge. A loop itself is a cycle. Right? So I think I might have made a small mistake in the definition. I might have made a small mistake in the definition. It's a separating vertex if it can be written as right. Okay, I made a small mistake in the definition. According to the definition I've written here, every vertex is a separating vertex. I need there to be at least one edge in each of these GIs. Otherwise, I can take the graph union the vertex and every vertex would be separable. Okay, so the edge set of GI is not empty for I in 1 and 2. There has to be at least one edge, otherwise I can just take the graph and union it with the same vertex, and that will be a separable so that will be a separating vertex. Okay, so I need there to be at least something in the graph apart from the vertex. Okay, so sorry about that. So now, as per this modified definition, let EI be any edge in GI incident at vertex V. Okay, because the graph is connected, you will find at least one edge incident at the vertex V in each of G1 and G2. Okay, so this is supposing one of them is a loop, then you are done. If either E1 or E2 is a loop, then done, right? Because there is no cycle containing both of them. Okay, so now suppose that they are not loops and they are just regular edges, or as we call them, links. Okay, now can they participate in a common cycle? What do people think? Can E1 and E2 participate in a common cycle? Anyone? No, exactly, right? If you have a cycle containing E1, well, it will have to go like this and it will come back to this vertex, right? Because it has to come back to that vertex eventually. But the moment you do that, you've completed the cycle and now you cannot use E2 anymore. Okay. So otherwise done as well. Okay, so in both cases you can just finish the proof, and I'm not writing down all the details, but it's evident. So let's prove the other direction. So now we are assuming that the graph is non-separable, and we want to prove that any two edges participate in a common cycle. Assume that G is non-separable, and let E1 and E2 be any two edges of the graph. Okay, so now we are actually going to use a trick. It almost seems a bit like cheating, but it's not. So the idea is to use theorem 5.1. We will use theorem 5.1, which says that any two vertices belong to a common cycle. But we want to use that to prove that these two edges belong to a common cycle. Okay, so here is the idea. We are going to define an operation on a graph called subdividing an edge. Okay, and I won't write down the rigorous definition. I'll just show you an example. Okay, so supposing I have this graph, let's say, okay, what I want to do is I want to subdivide an edge. So let's pick one edge, E, and I will subdivide it using one vertex. What I mean by that is you have the same graph, but that edge will be replaced by a path of length 2. Or another way to think of it is you are inserting a vertex on that path, or you are subdividing the edge using one vertex. Okay, you can also subdivide by putting more vertices, but in this particular proof we just want to subdivide it one time, so by inserting one vertex on that path, on that edge. Okay, so replace E by a path. That is the same as subdividing an edge E. Okay, so let's look at that graph. So what I'll do is here I'll subdivide both the edges E1 and E2. So this is my graph G, and what we will do is we will get a graph H by subdividing E1 and E2 both. So let me put the subdivision vertex like this, V1 and V2. H is obtained from G by subdividing each of E1 and E2 by inserting one vertex, V1 and V2 respectively. Okay, and I'll give you one exercise. If you subdivide an edge, the resulting graph will also be non-separable. So this is an easy exercise. If G is non-separable and H is obtained from G by subdividing an edge. Let me just think about this. Can I subdivide a loop? Does it make sense? Let me think about this. Supposing I give you this, subdivide. Okay. I don't know for sure. I'll have to think about this, but it doesn't seem like this should cause any problems. Anyways, let's refrain from that. Let's not get into things we don't need. Subdividing a link. Okay, so a link is an edge which is not a loop. I don't even know if we need subdivision of edge. We just need subdividing a link. Okay, good. So if you subdivide a link, which is an edge that is not a loop, then H is also non-separable. Okay, so in other words, if you apply this exercise, then the graph H here, which you get by subdividing two edges, is also going to be non-separable. Okay, so H is non-separable. And now we can apply theorem 5.1 to H. So if we apply theorem 5.1 to H on the vertices V1 and V2, then we know that V1 and V2 belong to a common cycle in H, right? Because the graph is non-separable, it cannot have any cut vertices. And the graph has at least 3 vertices because we have introduced 2 subdivision vertices, V1 and V2. So the graph H has at least 3 vertices, right? And it has no cut vertices. And so we can find a cycle in H. But if you find a cycle in H, you can also find a cycle in G, right? Because any cycle in H has to look like this. It has to use those 4 edges. And so if you look at the image of that cycle here, essentially you get a cycle containing the edges E1 and E2. Okay, so you are really using this exercise here, which is that when you do subdivision operation, the non-separability is preserved. Okay, and using that, you just apply theorem 5.1 and you're done. Any questions or concerns? So we get a cycle in G containing E1 and E2. Okay. All right. Let's see. So I think we already tell you what I'm going to do in the next. We will on Monday. We will discuss 2 decompositions of graphs. So the first one is going to be something that perhaps all of you may have seen in a previous course on graph theory. It's called the block decomposition. So what you do is you break a graph into smaller graphs, which are the maximal non-separable subgraphs of that graph. Often these are called bi-connected components or 2 connected components, but we will use the terminology from Bondi and Murthy, non-separable subgraphs. Okay. So that is a decomposition. Let me just give you a glimpse of it. So decomposition as in, it is a partition of the edge set. That's one way to think about a decomposition. A decomposition of any, let's say, connected graph, because we don't care so much about disconnected graphs, into its maximal non-separable subgraphs. And I am assuming that most of you have seen this in a previous course. So I will not be going into too many details. I'll probably just show you by example and skip the proofs. Okay. One thing you might want to do is you might want to go through this example, this big example that we have here, and think about the block decomposition of G. So think about the maximal non-separable subgraphs of this graph. Okay, and that is exactly the block decomposition of the graph. Okay, and a second thing I want to do is, now I want to take a non-separable graph and I want to look at what is called an ear decomposition. And so those of you who took my previous course, you would have already seen this. Ear decomposition, which is a decomposition for non-separable subgraphs or non-separable graphs. And this one it's good to think of both of these as induction tools. They are both induction tools for proving graph theoretical statements, and you will see applications of these either in the lectures or on the assignment too. Okay, so that's the plan for Monday. I'm hoping to finish both of them on Monday and start with chapter 9 of Bondi Murthy on Tuesday. Okay, all right. Are there any questions, concerns? Yes.
So can you go over the first part of the proof of theorem 5.2?
Okay. Theorem 5.2, the first part. Yes.
Yes.
Okay. So what is the part that you would like me to go over here? The whole?
So we proved the contrapositive, right?
Right. Yes.
And I can't understand the diagram.
Okay.
Correct.
Okay. So we know that the graph is separable. So let V be a separating vertex. Okay. Yeah. And now, by definition of separating vertex, the graph G can be written as G1 union G2, such that the only common vertex between them is the vertex V.
Okay, sir.
Right? And there are no common edges between them. And each of them has at least one edge, right? Okay. So then I took two edges, one in the graph G1, incident at vertex V, and another in the graph G2, incident at vertex V. Right? I can always do that because the original graph is connected. So both of these subgraphs will also be connected. Right? In particular, there has to be an edge incident at the vertex V. Does that make sense?
Yeah, that makes sense.
Right. So then we dealt with both of these edges. If either of them is a loop, then you are done. And if they are not loops, then again you are done. You cannot have a cycle containing both of those two edges. Right. So I was very brief here, but hopefully this part was clear. If not, we can go over it again.
Okay, so I think it's fine now.
Okay, thanks, Joe. Any other questions or concerns? So again, both of the proofs we have done today, 5.1 and 5.2, I have followed the text exactly. Sometimes I present different proofs, but in many cases, I might just choose the same proof and present it in a different way, perhaps. Okay, any other questions or concerns? It's 10:55. I'm here for another 5 minutes. So just out of curiosity, how many of you have not seen block decompositions before? I just want to get a sense of how much into details should I be going. Joe, yes? You haven't seen block decompositions?
Yes, sir.
Right. Sailash as well, okay. Okay. Anyone else who hasn't seen? Sailash, did you want to add anything else? Okay, thanks. Okay, so I will not go into it in too many details, but you can also just read about it in the text or in one of the reference books before the next lecture. I will probably skim through it really quick and just address whatever questions or concerns there may be. Okay, but it's a fairly straightforward thing. And if you just think about this example, try to think about the maximal non-separable subgraphs in this graph G. And that should be a good exercise to already get started. So for many problems in graph theory, you can first of all restrict yourself to connected graphs. Then you can often restrict yourself to non-separable graphs, or also called biconnected or two-connected graphs. And that's one of the reasons that these decompositions are really crucial, because instead of looking at all graphs, you just need to look at graphs that are sufficiently connected. Okay, and but the problem then is that you need some kind of induction tool for proving theorems for these classes. And the first such example we are going to see is ear decompositions. It is an induction tool for non-separable graphs. Okay. And we will be seeing more such induction tools in the connectivity part of this course. Okay, and we will see applications of such induction tools throughout the course. I also like to call these induction tools generation theorems, and I'll explain why. So this is going to be our first generation theorem. Girija, can you hear me?
Yes.
Okay. Could you please stay back after the meeting if you have some time? I'd just like to
I
have a
have
chat.
a meeting at 11. I have a meeting at 11.
Then I'll just catch up with you later. Thanks.
Okay, sure.
So I'm gonna stop recording now.